In 6.2, we're going to learn one new way to use the integral notation, and we're going to learn a technique we can use to greatly increase the number of antiderivatives that we can find. So we have to start with a definition for an indefinite integral. So far, every integral that we've seen has limits, a lower limit and an upper limit, to tell us over which x values we're going to find the area under the curve that's inside the integral. We can use the integral notation without limits, in which case we call it an indefinite integral, and all it means is find an antiderivative of the integrand. So, for example, this first guy, if I ask you to evaluate the integral of x squared minus sine x, what that means is find an antiderivative for x squared minus sine x. So I'm going to do that like this. That's equal to find the antiderivative of x squared, I'm going to add 1 to the exponent, x cubed, divide by the new exponent. Sine x, I'm going to have to think in my head, what would I take the derivative of to get sine x as the answer? Well, the derivative of cosine is negative sine, and that's actually what I have here is negative sine, so I'm going to say plus cosine of x. And I don't have enough information to figure it out, but I know that there might have been some number added or subtracted here, so I have to include the plus c. And the good news is you can always check your answer to an indefinite integral problem. We're going to do that by taking the derivative of our answer. So I'm going to find d dx of x cubed over 3 plus cosine x plus c, and I'm going to check that I get the integrand I started with. Well, the derivative of x cubed over 3 is 3x squared over 3. The derivative of cosine x is negative sine of x. The derivative of c is 0. And that simplifies to x squared minus sine x, which is what I started with as my integrand, which tells me that this answer that I got must be 100% correct. Okay, so 2 important indefinite integral facts. If you forget the plus c, you will not get full credit. It's critical. And a second fact, which is going to be important as we learn this second half of chapter 6 or section 6.2. In first year calculus, we only ever use integrals that have one variable. Now, sometimes you'll have another letter, a second letter inside your integral, but you've been told that it stands for a constant. So that's a constant, but we only ever integrate when we have one variable. So make sure you don't accidentally try to evaluate an integral that contains 2 variables. So super quick example to show you what I mean. If I want to evaluate the indefinite integral of 1 over 1 plus x squared dx, that happens to be a function that I recognize as the derivative of inverse tangent. So this answer here is not so bad. That's inverse tangent of x plus a constant. I can check my answer by taking the derivative of my result. The derivative of inverse tangent of x is 1 over 1 plus x squared. Plus the derivative of c is 0. And when I take the derivative of my answer, I do in fact get what I started with. That's my clue that this is the correct antiderivative. It's the correct result of the indefinite integral I started with. No problem. You're going to see lots of questions like that. Probably see one just like it on your AP test. Look at example 3. I've been asked to evaluate the indefinite integral of 1 over 1 plus x squared dt. Big difference. That's an integral that contains 2 different variables. X and t are both variables. They do not match. Unless somebody gives us some information that helps us change the t into an x or change the x into a t, we will not be able to evaluate this. So I would say cannot be evaluated. Now, I've been known to put problems on tests like this to make sure you're paying attention that the variables match. On the AP test, they will never do this. If on the AP test you end up with an integral that has 2 variables in it, that means that something you did along the way didn't work out right. and it's going to be your job to go back and fix the integral so it has one variable in it.